Hello and welcome to Fun Facts Online, the show that plugs you into the science and stories shaping our world. Today, we're talking about fire. Not just any fire, but the colossal, terrifying wildfires that are becoming an increasingly common and destructive feature of our changing climate. We've all seen the images. Hillsides glowing orange, smoke choking the sky, entire towns reduced to ash. When we think about the cause, we often picture a lightning strike or a careless campfire. But what if I told you that one of the biggest risks comes from something we rely on every single day? Something that powers our homes, our hospitals, and our entire modern lives. I'm talking about the electrical grid. And what if I told you that to prevent these catastrophic fires, the people who run the grid are sometimes forced to make a decision that seems completely counterintuitive? To intentionally plunge millions of people into darkness. This strategy has a name, a Public Safety Power Shutoff, or PSPS. It's a high-stakes gamble, a desperate measure to prevent an even greater disaster. But it comes at a massive cost, creating a complex web of engineering puzzles and severe economic pain. Today, we're going to pull back the curtain on this controversial practice. We'll explore the incredible technology being deployed to make these decisions, the devastating ripple effects when the lights go out, and the innovative solutions that might just lead us to a safer, more resilient future. So stick around as we de-energize the myths and power up the facts behind the fight against wildfires. So how exactly does the very system that brings us light and energy become a fire starter? It's a question of physics, weather, and aging infrastructure. Imagine thousands of miles of power lines strung across vast landscapes, often over rugged, remote terrain covered in dry grass and trees. Now, add in the perfect storm of wildfire conditions, scorching temperatures, low humidity, and most importantly, high winds. These winds can be relentless, causing the power lines to sway violently. They can slap against each other, creating a bright, hot arc of electricity. They can whip tree branches into the lines, or even knock entire trees over, causing the lines to fall to the ground, spitting sparks into the dry vegetation below. It's not just about lines touching things, either. The equipment itself can be a source of ignition. An aging transformer or a faulty switch can overheat and fail, sending molten metal and sparks flying. These aren't just hypotheticals. Utility equipment has been identified as the ignition source for some of the most destructive wildfires in recent history. Faced with this terrifying reality, utilities are in a constant battle against the elements in their own infrastructure. The decision to implement a public safety power shutoff is essentially a declaration that the risk has become too high. It's an admission that under certain extreme weather conditions, the safest grid is a grid that is turned off. But how do they know when to flip that switch? That's where the engineering gets truly fascinating. Deciding to cut power to hundreds of thousands of people is not a decision made lightly. It is a calculated, data-driven process that represents a massive balancing act. On one side, you have the immediate and certain disruption of a power outage. On the other, the potential for a catastrophic, multi-billion-dollar wildfire that could cost lives and destroy communities. To navigate this, utilities have assembled a sophisticated arsenal of technology and predictive science. It all starts with the weather. But we're not talking about just checking the forecast on your phone. Utilities employ teams of meteorologists and use advanced weather forecasting models that provide incredibly granular detail. These models analyze a torrent of data, wind speed and direction, down to the level of individual canyons, humidity, temperature, and crucially, the moisture content of the vegetation. They use tools like the Wildfire Hazard Potential Index to create detailed risk maps, pinpointing specific circuits and power lines that are most vulnerable at any given moment. This isn't just about predicting the weather, it's about predicting fire. But seeing the risk is one thing. You also need to see what's happening on the grid itself, in real time. This is why the modern grid is becoming increasingly intelligent. Utilities are deploying a vast network of advanced sensors on their poles, wires, and transformers. These sensors act as the grid's nervous system, constantly feeding data back to a control center. They can detect the strain on a power line, the temperature of a transformer, or even use cameras and LiDAR to spot vegetation getting dangerously close to the wires. This allows operators to see a problem developing before it becomes a disaster, and when a problem does occur, the grid needs to react in milliseconds. This is where we see some of the most impressive innovations. Take a device called a recloser. A recloser's basic job is to act like a smart circuit breaker on a power line. If a temporary fault occurs, like a tree branch brushing against a line and then falling away, the recloser will quickly interrupt the power and then try to restore it a moment later. This prevents a long-term outage from a temporary problem. But in high fire risk conditions, that brief burst of electricity when the recloser tries to restore power could be enough to start a fire. So, modern reclosers are now being built with flexible, adaptable settings. Operators can, in real time, change how the recloser behaves based on the weather. On a high-risk day, they might set it to one-shot mode. If a fault occurs, it cuts the power and leaves it off, preventing any chance of re-energizing into a fire. Alongside reclosers are new types of fault interrupters and fuses. Some are designed to be sparkless, containing any electrical arcing within the device itself, like a tiny, contained lightning strike, preventing sparks from reaching the dry landscape below. Another clever device is the Spark Prevention Unit, or SPU. These focus on surge arresters, which are components that protect the grid from lightning strikes but are prone to overheating in hot, dry weather. An SPU acts like a personal bodyguard for the surge arrestor. It monitors its thermal load, and if it detects an overload, it automatically disconnects the arrestor before it can fail and spray sparks. This move from reactive to proactive protection is being supercharged by artificial intelligence. AI and machine learning platforms are becoming indispensable tools for wildfire mitigation. Imagine trying to make sense of data streaming in from thousands of sensors, weather satellites, and drone inspections. It's an impossible task for a human, but an AI can sift through these vast data sets, identify subtle patterns, and predict potential ignition points with frightening accuracy. Some of the newest AI-driven systems are even tackling one of the most difficult challenges in grid safety: detecting high-impedance faults. This is a type of fault that's notoriously difficult to spot with traditional methods, often occurring when a live wire makes poor contact with the ground or a tree. It doesn't draw enough current to trip a standard breaker, but it can create persistent, dangerous arcing. New AI solutions can now analyze the electrical signature of the grid and detect these stealthy faults, allowing the system to de-energize the line in seconds. Finally, there's the long-term, brute force solution: grid hardening. This is about physically rebuilding the grid to be more resilient. The most effective, but also the most eye-wateringly expensive, strategy is undergrounding, burying power lines. It's estimated to reduce the risk of ignition by up to 99%, but the cost can run into millions of dollars per mile. It's a slow, laborious process that can take decades to implement across a vast service area. Other hardening measures include replacing traditional wooden poles with steel or composite ones that are more fire-resistant, and coating power lines with more durable, insulated materials. All these technologies, from predictive AI to stronger poles, are designed to make the grid safer and reduce the need for public safety power shutoffs. But for now, they remain a necessary evil. And when the call is made to turn off the power, the consequences begin to ripple outwards immediately. The engineering behind a PSPS is all about preventing a future catastrophe. But the moment the switch is flipped, a very real and immediate crisis begins for the communities left in the dark. The economic fallout of a power shutoff can be severe and widespread, hitting businesses, families, and critical infrastructure all at once. For businesses, especially the small businesses that are the lifeblood of many rural and suburban communities, a planned outage is a body blow. The most immediate impact is lost revenue. A study of one multi-day PSPS event in California's Sonoma County estimated a staggering loss of approximately $105 million in economic output. That's $105 million that didn't go to wages, supplies, or local investment. For a small retail shop or a local contractor, a few days of no power can be the difference between profit and closure. Operations grind to a halt. In our hyper-connected world, no power often means no internet, no point-of-sale systems, no phones. But for some industries, the problem is far worse. Think about grocery stores, restaurants, and wineries. Their entire business model depends on refrigeration. A prolonged outage means thousands of dollars of spoiled food and product literally being thrown into the dumpster. The burden on households is just as profound. PSPS disrupts daily life in 1,000 small ways. You can't cook a hot meal, you can't do laundry, you can't charge your devices. If you work from home, your livelihood is on hold. The food in your own refrigerator starts to spoil. While these are major inconveniences for many, for some, they are life-threatening emergencies. The shutdowns disproportionately affect low-income households, who may not have the resources to buy a generator or eat out for several days. But the most acute risk is to vulnerable populations. Tens of thousands of people rely on electricity for critical medical devices, power wheelchairs for mobility, nebulizers for breathing treatments, dialysis machines, and ventilators. For these individuals, a power outage is not an inconvenience, it is a direct threat to their health and survival. Utilities have programs to notify these customers, but the responsibility often falls on individuals and families to have robust and often expensive backup plans in place. Beyond the direct impact on homes and businesses, power shutoffs reveal just how fragile our interconnected systems are. The electrical grid is a foundational infrastructure. When it goes down, it can trigger a domino effect of cascading failures. Cell phone towers often have backup batteries, but they may only last for a matter of hours. As a shutoff drags on, you can lose cell service and the ability to call for help. Municipal water systems often rely on electric pumps to maintain pressure and supply water to homes and, ironically, to fire hydrants. Without power, water service can be disrupted. Even something as simple as traffic lights go dark, creating chaos and safety hazards at intersections. In essence, a public safety power shutoff, designed to protect a community from one disaster, can inadvertently create a series of smaller, overlapping crises that strain emergency services and leave the community feeling isolated and vulnerable. The immense challenges and costs of grid de-energization have, however, become a powerful catalyst for innovation. Faced with this difficult trade-off, engineers, utilities, and communities are actively searching for a more resilient path forward. The goal is not just to get better at turning the power off, but to build a future where we don't have to. One of the most promising solutions gaining momentum is the concept of the microgrid. A microgrid is essentially a localized, small-scale electrical network that can connect to the main grid but also operate independently, or island itself, during an outage. Imagine a small town, a hospital, or a fire station powered by its own local source, like solar panels and a large battery system. When the utility announces a PSPS for the wider region, this microgrid can disconnect from the main grid and continue to provide power to its local customers. This keeps critical facilities online, allows businesses to operate, and provides a safe haven for residents. It's a way of building pockets of resilience that can weather the storm of a larger blackout. Taking this concept a step further, some utilities are exploring what are known as remote grids, particularly for very sparsely populated, high fire risk areas. Instead of maintaining dozens of miles of vulnerable power lines to serve just a handful of customers, a utility might instead build a completely standalone power system for that small community. This system, often powered by solar and battery storage with a backup generator, provides cleaner and more reliable electricity. The old, risky power lines can then be decommissioned entirely, permanently removing that fire risk from the landscape. It's a surgical approach to solving the problem, replacing long, fragile connections with robust, local independence. Utilities are also rethinking the fundamental design of the grid itself. For decades, many parts of the grid were built like a tree, with a main trunk and branches. If there's a break on a major branch, everyone downstream loses power. The future is in creating more looped systems. A looped grid provides multiple pathways for electricity to flow. If one section needs to be de-energized for safety, power can be rerouted around the shutdown area, much like a traffic detour, minimizing the number of customers affected. This is being combined with investment in new technologies that can rapidly limit the amount of energy released during a fault, a concept known as fault current limitation. This reduces the energy available to create an arc or a spark, further lowering the risk of ignition. Finally, we come back to the trees. A huge portion of utility-related wildfires are caused by vegetation coming into contact with power lines. Traditional vegetation management often involved cyclical tree trimming, which is labor-intensive and can be imprecise. Today, utilities are using advanced technology to be far more strategic. They use aircraft and drones equipped with LiDAR, a technology that uses lasers to create highly detailed 3D maps of the terrain. This allows them to precisely measure the distance between every tree and every power line in their entire service area. They combine this with satellite imagery and AI analytics to identify the fastest-growing species and pinpoint the specific trees that pose the greatest risk, allowing them to focus their trimming efforts where they will have the most impact. So, where does this leave us? The decision to shut off power to prevent a wildfire is one of the starkest examples of the difficult choices we face in an era of climate change. It is a blunt instrument, born of necessity, that pits public safety against economic stability and individual well-being. As we've seen, the engineering to make this decision is incredibly sophisticated, leveraging everything from predictive weather modeling and AI to intelligent grid sensors and spark-proof fuses. It is a high-stakes balancing act performed by grid operators in real time. But we've also seen that the consequences of these shutdowns are profound, disrupting lives, crippling businesses, and disproportionately harming the most vulnerable among us. The path forward cannot be about simply accepting blackouts as the new normal. The future of a fire-resilient power grid lies in a multifaceted approach. It will involve a combination of smarter, more agile technology that can detect and isolate faults in a fraction of a second. It will involve the long, expensive process of hardening our infrastructure, burying lines where we can and building them stronger where we can't. And perhaps most importantly, it will involve a fundamental shift towards a more decentralized and flexible grid, with microgrids and remote grids creating islands of energy independence that can keep the lights on for critical services and communities, even when the larger grid has to go dark. The challenge is immense, but the innovation it is driving is creating a clearer vision of a future where we can keep the power on and our communities safe from fire. Thank you for tuning in to Fun Facts Online. Join us next time as we explore another fascinating story from the world of science and technology.